Hello. This first video is about engaging with math and numbers, and also on the topic of the beauty of math and numbers. Now, one cautionary note right from the beginning is if the only way you engage with numbers and math in general is through things that you consider beautiful, then you're going to miss the best parts. So, by way of example, I would like to talk about three specific famous numbers and one famous equation as well. These do come up a lot. The first one, of course, pi, the circle constant, defined quite simply as the ratio between the circumference of a circle and its diameter. And of course, the great thing about this is it doesn't matter how big your circle is, the ratio is still the same. Oh, and by the way, I'm confident right up until about here. From here on, well, I might be right, but I'm definitely confident up to here. So now this is a little bit overrated. I mean, it is everywhere in math, but it is a bit overrated. And here's why. So if you're measuring something circular, you can use a pair of calipers and you just read off the diameter. So that is nice. But when we talk about circles in math, we typically define them in terms of their center and the radius. In other words, the distance of every point on the circle from the center. And since this is the case, there's a very good argument to be made that, and I'm definitely going to be linking something in the comments below, that the better circle constant is actually 2 pi, which is again the ratio between the circumference and the radius. All right, so that was the circle constant, and don't worry, there will be plenty of videos involving circles later. So for now, I would like to move to the next famous number. This this thing at the bottom is the number e. And it is definitely an underrated number. And it's basically just about exponential growth. In particular, if you look right here, this is the function 2 to the n. So at each step, you double. And what's special about 2 to the n in particular, as opposed to, say, 3 to the n, 1.4 to the n, whatever, is that when you double, the gain is exactly 100%. And in particular, when you double from 1 to 2, you get a line through there that has a slope of exactly 1, which again corresponds to 100% growth. And in fact, it means that when you have two things, then at the next step, you gain two things. If you have four things, then you gain four things. You have eight things, you gain eight things. And the difference every single time between 2 to the n plus 1 and 2 to the n is exactly 2 to the n. So this is a very special exponential growth function. It's just double, double, double. 100% growth every single step. Now, a lot of the time, though, we like to have our functions defined for all real numbers, not just whole numbers, not just counting double once, double twice, etc. I know, thrice, it's a weird word. But we want to do something continuously. And you may have seen this before from like pre-calculus compounding interest. And when you try, compounding infinitely many times, you end up with this number e. And while it seems like an abstraction, I mean, it is an abstraction, but it's not a huge abstraction because ultimately we're doing exactly the same thing we did over here. We just we're aiming for 100% growth. It's just that instead of compounding only at the end of the interval, we compound from the very beginning. So we're aiming for 100% growth, but we immediately start to overshoot. And that's all that's happening. We're aiming for 2, but we miss upwards. But because we are aiming in exactly this direction, so we're starting with 1 of whatever, and we have an instantaneous rate of change. The slope of the tangent line is 1. So we start with 1, we're changing at rate 1, 100% growth, just like this. The only difference is now we have a continuous function. But the story here is exactly the same. The rate of change, discrete, instantaneous, is equal to the function itself. So ultimately what that means is that E, it's kind of just 2's big brother. And it is one of the most ubiquitous numbers in math. And more than that, it's also one of the least arbitrary. It's the only number that does that job for continuous exponential growth. And last, we have a lot of people's favorite number, the one that really gets brought up when people are talking about math and beauty and stuff like that. And a lot of it is deserved. And that number is the golden ratio. Now, it's a bit of a wall of stuff on here, and that's a kind of par for the course with this number. I mean, you can define it in several ways. It's the diagonal of a regular pentagon, side length 1. Um, you may have seen a golden spiral. If I tried to draw it, I would ruin it. A very, oh, and of course, the Fibonacci number. It's a Fibonacci sequence. I mean, it comes up all the time when people are talking about that, and I'll get back to this in a moment. But a simple definition of the golden ratio is here we have a rectangle. We label this longer side phi, just Greek letter F, no particular reason that there's probably a reason historically. Anyway, so then we extend this rectangle to a larger rectangle by just drawing a square with this same side length. And we define phi so that it is the number such that this long side divided by this short side is the same ratio as this long side divided by this short side. And what we get is that phi over 1 is then equal to 1 plus phi over phi. So there's a nice algebraic definition, which leads to a few interesting properties right off the bat. One is if we just directly divide through, we get this one up here, which tells us that phi is a number that is equal to 1 plus its own reciprocal. That's an interesting bit of some symmetry right there. Now, if we cross multiply, move everything to one side, we get a quadratic equation. And a fairly simple one at that. I mean, there's not even a 2 in here. It's all the coefficients are 1, 1, and 2 negative ones. So it's a quadratic equation. It's a simple one, but it's not quite as simple as say x squared equals 2. It's just a bit more complex than that one. And that's going to be kind of important later. So this one we can solve with the quadratic formula. And we get this number, this exact answer right here. There's technically, a second root, but that one's negative, and well, we're definitely not looking for something negative. So this is the golden ratio. Exactly. And it's roughly equal to 1.618. Well, that's nice. Okay. Now, back to the Fibonacci sequence. So, we take two numbers, we add them together. We take these two numbers, we add them together. We take these two numbers, add them together, et cetera, et cetera, et cetera. We get each new number by adding the previous two. And one interesting feature is, well, let's divide these two numbers, 5 over 3, and you'll note that, well, it's 1 and 2/3, 1.6 repeating. Kind of close. If we take these two numbers over here, then we get a lot closer. I mean, we're almost at the thousands place, just a few of those off. And in fact, if we go farther and farther and farther, these ratios will approach the golden ratio. So it's here as well. And if if you have a thing for the golden ratio, you've probably also seen it come up in nature. Like take a sunflower, you look in or a pine cone, you look at the spiral pattern, you count the objects, different plants, different objects on the spirals, and you also somehow get this. um, and that one's a little less obvious as to why that's happening. Um, and to really go into that one, I would have to discuss something known called continued fraction expansions, and that would require a separate video. Ultimately, for me at least, the takeaway is that it's not some mystical number. Um, it's, I mean, it's really interesting, fascinating even, but one should be careful about the whole mysticism thing because it's not mysterious. It is, as I mentioned before, a simple number. In fact, it is a number that is simple enough to just do this with, but just complicated enough to have some really interesting behavior. You might even think of it as the simplest complicated number. You're just shifting forward in the series a little bit, and then you rewrite that quadratic equation with the powers of phi, where phi to the 0 is 1, then note you might have noticed some similarity already. And this is not a coincidence. The number, phi, is embedded not only in the general form of it, but in every aspect of the sequence. So it's not actually a coincidence that it shows up there as well. It always had to show up there. And again, it would take another video. There's actually some more really cool math in this. So yeah, the golden ratio is a nice, in it goes really nicely into a bunch of other cool things. So I'm not knocking it, but just don't mistake fascinating for inherently complicated or mysterious. It, it's it's what it is. Um, it doesn't have to be more. And finally, we have a lot of people's favorite equation, Euler's formula, specific case. And this one is often specifically touted as being a beautiful formula because it has like all of these fundamental numbers. It's got 1, it's got 0, e, I, and pi. I'll definitely mention a lot more about again, future videos. It's actually pretty fun stuff. But so yeah, it has all of these in one neat package. And I'm sure by now you have noticed the sarcasm in my voice because it, it is beautiful by a 17th century, I think, white male European mathematician standard. Um, okay, don't take the whole thing too literally, but back then, mathematicians did not like negative numbers. If they had a negative number on one side of the equation, they would move it right over here, just have a plus sign. And that's kind of exactly what happened with this equation. Here's a better way to write it. Here, now we have a negative one. Oh no, the horror. And here's what it means. All right, so what we have here is a circle, and we tend to measure the angle from the center in terms of the number of radii that we've traveled around here. And if you travel pi radii, well, note that, each 2 pi times r. So if you travel pi radii, you end up from 1 to -1. That's what it means. And here's an even nicer version. If we go 2 pi radii, aka tau radii, around, we get back to exactly where we started, i.e., e to the 2 pi I, or tau I, equals 1. That's it. It's just how far around this circle do we go? So the takeaway is there's a lot of cool stuff here. But if you only look at what feels beautiful, you're going to miss, again, you're going to miss the best parts. Anyway, so my next video going to be more about numbers in general. Yes, I will come up, and I hope you learned something. Bye.